Hello, everyone, and welcome to part 2 of our series, Tips and Tricks to Better Histology in Tissue-Based Research, a review of key factors influencing the quality of sections and stains. I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Leica Biosystems. For more information about our sponsor, please visit their site at leicabiosystems.com. So let's get started. I want to remind everyone that this event is interactive, and we encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. If you have any trouble seeing or hearing this presentation, just click on that support tab found at the top right of your presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. I'd like to welcome back our presenter now, Fiona Tarbet, a product manager at Leica Biosystems in Melbourne, Australia. For a complete biography of our presenter, please visit the Biography tab at the top of your screen. Fiona, welcome again. You may now begin your presentation.
Okay. Hi again, everyone. I hope you enjoyed the last session of Tips and Tricks to Better Histology. So today I'll be taking up where I left off and starting with all of the workflows post-embedding, post-tissue processing with embedding. Once again, just a quick disclaimer, these webinars are for educational purposes only, and they're not intended and should not be construed as medical, regulatory or legal advice. So once again, just want to set the scene for those who may have missed it, but just to remind everybody of what we're actually trying to achieve today. So the scene within histology laboratories, whether they be research or clinical, often face the same sort of problems, that we are in a really high pressure environment. We need to try and get tissues out in a shorter turnaround time to get results, which can sometimes lead to more problem blocks. We often don't have enough time to actually think problems through, or we don't get told about problems until at some time later, once everything is packed away. So there's often pressure for quick fixes. We may not have really experienced staff or time to fully train staff, and it can be difficult to have a conversation about what is actually a problem when the people that are assessing the sites may not actually be aware of some of the issues that labs face. Issues with resources, technological change, it can often be a real challenge. So the absolute aim is to produce high quality sections and stains in a minimum time from blocks that cut easily in a stable and prolonged storage, with accurate identification and labelling, with associated complete patient information in minimum time and consistently every single day. So this presentation is going to guide you through some of the key factors to achieve great quality, from embedding through to staining. So we start with embedding, and this is sometimes overlooked as a cause of sectioning difficulties. Some of the problems are very obvious if there's a large bubble in the wax or the tissue is not flat, therefore you don't achieve a full face. There's not enough wax around. Somebody has selected the wrong mould by the time you get to cutting. But the effect of careless embedding can be very subtle, and it can make cutting very difficult. So you need to orient the specimen carefully in regards to where the microtome blade is. And this is determined at embedding. So an awareness of how the block will be placed in the microtome in your particular laboratory is really important for the embedders to know. Here's just some examples. And just as a quick tip, always put, if you have soft tissues and harder tissues or mixed blocks, such as in an intestine, make sure your softer elements are facing the blade first. If you have really hard tissue like cervix, which is quite dense, again, make sure that the point of least resistance meets the blade before the larger tissue does to make smooth transition through the block. And similarly with skin, you might have a fat, an underlying fat layer leading up to quite a firm and dense epidermis. Again, make sure that the softer tissue meets the tissue first before you get into the harder tissues. So distortion during cutting is often an issue. So think of different causes of excessive compression when cutting tissue sections. You might think it is all to do with the blade, but there's actually a number of different causes here. There could be poor fixation. It could be poor processing. As we talked about in the previous session, the fixation and the processing has a lot to do with all of your downstream processes. So always consider, is the block actually the problem, or is the fixation processing a problem? You might have poor quality wax. You might have a block that's too warm, so you need to make sure that you cool that down. You could be cutting it too fast. The blade could be dull, or the blade is dirty. It's the facet surface is sticky with wax. The blade tilt is too great. Facet angle is too great. So think about some of the causes of distortion. So distortion occurs during the sectioning process. The section is compressed on its upper or outer face and elongated by the same amount on the inner face adjacent to the knife. The question is how much of this is recoverable. The amount of distortion is proportional to the section thickness. So the thicker the section, the greater the area affected by distortion. You might consider reducing the micron thickness of your sections. You also need to check on the facet angle. So usually between 22 and 35. The greater the clearance angle, the more distortion. Again, usually aim for between 4 and 9 degrees. And the less resistance to passage of the section over the facet surface, the less distortion the nature of the surface can vary between brands. So when you are thinking about which blade, make sure that you're using the correct blade for the job. So blades from different manufacturers will have different specifications. Usually you'd select a blade for your most routine work. A routine might be a blade with an angle of, say, 35 degrees. But then other blades might be more suitable. They might be treated with special treatment that is good for bones or for harder tissues. The other thing that's really important and is probably, again, overlooked by a lot of lab staff is to actually clean the microtome, but learning how to actually take apart the knife holder is really important. There are instructions, and like many, many instructions, people don't usually read them. But it is really important to have some idea, or at least even have a nominated person in the lab who does know how to correctly maintain the microtomes. There is an image here of microchatter, and again, this is often attributed to poor processing, when in fact it could just be that it's called chatter right through the block because it's a loose blade. So before you cut tissue, it needs to be cold. And that is so you do achieve the correct thickness. So there's various different methods different labs prefer. They might put the blocks in a freezer. They might use a cold plate at 4 degrees or down to -5 degrees, varies. The surface of melting ice is a very common practice, or some labs use a cold spray. There are other methods too if you've had slightly difficult blocks to either soak or soften before cutting. And there's a lot of different recipes, either commercial or ones that you can find and make up yourself. And this just helps with blocks that are perhaps a little bit too brittle, or they've still got some calcium in them, or they're just hard. But just remember the method of your soaking or softening, or just even keeping those blocks cold, can really cause changes in morphology. And here's just an example, one that we created ourselves. This is exactly the same block. The one on the left-hand side has been soaked in water for over 30 minutes. The one on the right didn't have water soak, just placed onto a cold plate and cooled down. And you can see the effect of water seeping into a block, even though clearly the block was well processed, but it does cause some distortion to the morphology. Again, you have a morphological change. You can see it in the block, you can see it in the microscope slide, and it's not due to the tissue processing. It's not due to the fixation. It's just simply that a block has just been left there a little bit too long and it's caused issues. Some common flotation problems. You may get contamination on your water bath. You may get cross-contamination if you have left two different sections. It could have actually come from grossing, just be aware. It's also quite common people leaving the tissue on the water bath at too high a temperature or for too long, which leads to overexpansion. Again, there's morphological change and differences down the microscope, which have got nothing to do with how well the tissue was fixed or processed. So just be aware of being really consistent, making sure that you cut one block at a time, making sure that you pick up the section in a timely manner. So you can see some of the issues that can happen. A bubble from flotation has resulted in the detachment of the section during staining. So where the tissue, it wasn't obvious when you cut the section or dried the section, there is still a bubble that will cause, and it could be a critical part of that particular tissue that you were looking at in downstream staining processes. So just some things to think about. Replace water regularly, always skim the surface between blocks, float sections from only one block at a time. Monitor the temperature carefully. Usually at about 44 degrees is a good temperature for a water bath. Look at what your wax temperature is and perhaps 10 degrees below the melting point, 5 to 10 degrees below the melting point is appropriate. Monitor flotation time carefully and always assess the section quality whilst floating out. So some common problems: mechanical damage caused by prodding with forceps or brush when trying to remove wrinkles. Think about some alternative methods if this is often a problem. You could consider a pre-cold water bath before the hot water bath, and this can sometimes be a control, particularly for more delicate tissues, or perhaps when people are just learning how to cut sections. Then it is something that you could consider is putting the section onto a cold water bath, dealing with the wrinkles there, and then transferring it onto a warm water bath for actual floating out. It's interesting to selecting the best section. So the first sections which are coming off from a chilled block are often a little bit thicker, but they often look like they're better because they're a little bit fatter, if you like. So the tissue looks better, but it's obvious it's not usually the best section to select. So again, be consistent with the sections that you are taking off, but consider the perhaps less, robust sections that are 2 or 3 along the ribbon, because they will probably be your desired thickness. So draining and drying sections. Very important. If they're not drained properly before drying, some areas may not flatten, and that's because there are water droplets that remain underneath the section. You can see that it's actually lifted, but it may look like there is something missing in the morphology, and you may not be able to make some diagnosis at that point because there's still some water that's caused this lifting. You often do get inconsistent draining techniques between microtomists, or sometimes in a rush to get slides into the stainer, that they're just not left long enough. So it is a really important point to just make sure that there's standardisation through here. But also think of the method of drying. I mean, again, speed is often an issue that people trying to race things through. Consider, are you using a hot plate? Is it the right temperature? Is it an appropriate method for your tissues? Does it have hot spots? And some tissues are particularly prone to the heat damage, such as hematopoietic tissue. So again, some examples here. You can see IHC done on a tonsil for the antibody CD3. So it wasn't properly flattened and drained before drying, so it resulted in lifting and therefore a distorted staining pattern. Also lifting, poor adhesion and folds have resulted in almost impossible to diagnose tissue staining. So moving on to the H&E stain. So the H&E stain is the most common or routine stain in laboratories throughout the world. So we'll just be going through some of the theories and some of the issues to look out for in achieving a really good H&E stain. So achieving consistent high quality is challenging. There are a lot of quality assurance programs that can benchmark your stain, and they can be very useful. You could find them online or join a quality assurance program. And participation can often be a requirement for laboratory accreditation. Certainly in a clinical setting, that would be true. So some key questions. To ask yourself how to resolve some of the issues around your H&E, do you depend on your pathologist or senior scientist to tell you when there's something wrong? Do you use a suitable control slide? Do you look critically at every control slide? Does your staff know how to assess an H&E for quality? At what stages do problems usually arise? And what can you do about them? All of these questions can also be applied to any special stain or to any IHC stain, fish stain as well. So for an H&E, choosing a control slide is really important. It's very important to have a control slide to monitor your stain, but you need to therefore make sure it is robust. So it is a good idea to have a range of tissues that demonstrate just different aspects of stains. They should be cut to your normal thickness, and the multi-blocks do give you an opportunity to really do a complete assessment. But if you do select just one tissue as your control, make sure that it has got some different elements there, such as gut. So you might have mucosa, you've got some collagen, you've got some muscle, which all will display some different staining patterns, and you can really assess how well your H&E is staining. So, and why it's particularly important to select something like a bowel specimen is you might select something like placenta, which is a notoriously easy tissue to stain and often stains really well, even though your actual stain is not as good as it should be. So knowing what to look for. So there are some key things that you would be looking for. So you need to look for some well-defined nuclear detail that shows both coarse and fine hemochromatoin and nucleoli. Looking for mitotic figures, they do stand out very well. They should stand out very well in a good stain. Collagen fibres, both coarse and fine, should be well differentiated and a different differentiation from the smooth muscle. Good cytoplasmic texture. Look at the luminal margin and look at basement membranes. Nissl granules in autonomic ganglia, so they should be clearly defined and basophilic because of the large amount of ribosomes. So again, standing out clearly in your smooth muscle, in between your smooth muscle. Eosinophil granules are strongly stained. Cytoplasmic basophilia, you can look at plasma cells in your lamina propria as well. Endothelial cell cytoplasm is well defined and red blood cells stain brightly and uniformly. You can create your own scoring, H&E scoring matrix. We have created our own scoring matrix, and this will be delivered to registrants from this webinar. But basically what we've done is just look at some different criteria to look for hematoxylin, for Eosin, and actually where to look. And then we have a 3-point scoring system, and just this has just some examples of what would be a good, what would be a bad, what would be a satisfactory stain. So in this way, you can keep a record of how well your staining is going, and is there any sort of deterioration. You could consider scoring your controls, or you can use this as a way of measuring whatever tissue processing you're looking at, or whatever your experiment is actually trying to achieve. So again, think of some different causes for a weak hematoxylin stain. So we're going to go through some of the fundamentals of the H&E. H&Es for hematoxylin and Eosin stains are either regressive or progressive stains. We're going to be looking at just some of the areas within the stain and some of the common problems that you might find there. So first of all, the dewax. It's the very first step. So if there is residual wax, it can cause staining faults because the stain cannot access the tissue. Some of them might be very obvious, like large areas are not stained, or some might be very subtle. So wax removal is slower when the slides are cold. And again, this is something that if you cut, particularly say control slides or slides the night before, stain them the next day, think about when you optimized your dewaxing. Was that done on slides that have just been warmed, slides that have come out of an oven, or slides that have been left cold? Either your dewax was optimized to warm slides and cold slides just will not dewax correctly. Wax removal is slower when sections are thicker. It's slower with old sections. Different solvents remove wax at different times. Think about, are you using a substitute, a xylene substitute or xylene? That might take a lot longer if it's a xylene substitute. And also, when did you last change your solvent? Because excessive wax will prevent good dewaxing. So here's an example, and in the previous session I talked a little bit about blue hue and talked about that can be caused by excessive water from underprocessing or contamination. Here is another example where we might call blue hue when it's actually a result of the wax still left in the tissue, and therefore the stain was not able to penetrate through. Another example here is an unstained area due to residual wax in a tonsil with an H&E stain. It's always worth cutting the section again if you do see some issue. As you can see on the left, there are two eosinophilic patches that do not exist in the same tissue on the right. And that's purely because there is residual wax left in the tissue. So moving on to hematoxylin. So there are a number of different commercial hematoxylins in use, or formulations that you can make up yourself. Less common nowadays, but certainly very possible. Recipes are freely available. And you can see this is just a chart that was from the Royal College of Pathologists in Australia, where different laboratories have different preferences for whatever reason, and the marks vary, and that can be because of the laboratory or because of the stains themselves. So some stains are better for progressive stains and others are better for regressive stains. And again, just consider what sort of stain you are planning to do. A progressive stain is where you stain up to a point, your hematoxylin, and then you stain with Eosin. A regressive stain is where you overstain your hematoxylin and then remove until you're at the point where you have good nuclear staining. It is a preference. There's pros and cons for either a progressive or regressive stain, but just think about what your formulation is and whether it is actually more suitable for a progressive or a regressive stain. So some common problems. These are two control slides, so cut the sections of the same thickness. They were stained on an autostainer using identical protocols, but there was a gap of 1 week between the staining of the two slides. And this is where your scoring can come into it, but a quick glance can show you that there's a very big difference because the stains have gone off over the week. So hematoxylin needs to be oxidised into hematin. If it's over-oxidised, then it becomes a colour... hang on. Over-oxidation. I went too slow. So if it's over-oxidised, it can actually turn into a colourless product that can't then be combined with your mordant for staining. So again, if a hematoxin is left too long, and if it's a commercial one, they will be ripened to a certain level, but there's still oxidation that occurs while the hematoxin is in either a staining instrument or a series of baths. So just remember that if that is left too long, it will over-oxidise and become non-usable. So I mentioned earlier, the hematin needs to be combined with a mordant, and this combines to a dye lake. The most general aluminium is for its blue, but you may have an iron mordant, which is particularly useful for special stains. You might think of a trichrome when there's acids used as steps within the stain. Then an iron might be more suitable than an aluminium, but aluminium is the most common. You need to think about the effect of the pH on your complex, because again, wrong pH will result in the wrong colour. Consider the hematoxin will be progressively diluted by water carryover. Depending on your water, this will alter the pH, and so not only dilute the actual hematoxin, but it will alter the pH and may result in poor staining. It is progressively oxidised in the staining bath, and the oxidation products do not contribute to staining. So the effect of staining will depend on the amount of unoxidised hematoxin in the solution, which can be progressively oxidised as the stain is used. Most commercial H&E or hematoxin do have stabilising agents to slow that oxidation. The other thing to consider is nowadays most labs use automated stainers. So whatever the recommendation from the manufacturer on the either stainer or from the hematoxin itself, think about what they recommend in terms of times of protocols, because the design of the stainer, the size of the surface area that is available for oxidation of the reagent will contribute to how long that hematoxin will last on the instrument. This is the same for the surface area of the staining bath, if it's a staining bath on the bench, as much as with a staining instrument. Think about where the hematoxin is stored. The pH of alum hematoxin is important, as we went through, and it is adjusted to favour the staining of the nuclei. So again, the progressive will have you would add a slight amount of acid, or they're slightly more acidic for a progressive stain, and that is to make the stain more selective for the nuclei. As an example, citric acid is added to the maize hematoxin to drop the pH, and it's a feature of progressive staining. Moving on to the differentiation. So differentiation occurs in a regressive stain where you need to be taking out that excessive amount of hematoxin and just leaving the elements you do want to stay with hematoxin, the nuclei, well stained. So the variable acid differentiation can affect the consistency. And again, because there's carryover in either a bench or in an instrument, you will find that they become progressively diluted. And so the optimal differentiation times can change. And this is particularly an issue if you have quite an aggressive time. So with acid-alk with hydrochloric acid, that is fast. You need to be considering how your protocol has been optimized. So you can dilute the differentiated times, the differentiator times so that times can be lengthened and add a bit more control and consistency. Or you can use what is commonly called as a clarifier rather than a differentiator. And this is using a different acid, usually acetic acid or some weak acid, so that it actually gives you more time and more control. You do need to blue after use of any acid alcohol. So the water wash. So the bluing can happen in tap water if the tap water happens to be quite alkaline. So just be aware of what the pH of your tap water is, because it can vary quite a lot. This is particularly important in all steps of your stain. If you're using tap water, changing the pH in any step can have an effect. So you could use Scott's tap water substitute, again, either commercial or make up your own. Ammonia water is commonly used. And this is just purely to blue the nuclei, particularly after both progressive and regressive hematoxin. So eosin, again, the pH of eosin is very important, whether you use an aqueous eosin or an alcoholic eosin. So generally around pH 4 is good. So if the pH rises, the staining becomes weaker, and the eosin will therefore, even though it appears to be staining, it will wash out during the post-eosin rinses. Residual alkali from bluing or from your tap water can cause weak and patchy staining. Be aware. You can add several drops of acetic acid to eosin, and that does improve the staining, and this might give a little more life to your eosin if it's dropping off too quickly because of carryover. However, eosin does display differential staining, and that's what you want. That is desirable and achievable. If you do have too acid an eosin, if you've added too much, you will get stronger staining, but you lose the ability of eosin to actually differentiate in the different elements that it needs to. So clearing, you must make sure that there is no water left before you apply a cover slip. So clearing really needs to be, you need to make sure that those solutions are changed and often. So the final change of absolute alcohol must be uncontaminated. There must be sufficient changes of alcohol and sufficient time to complete dehydration, and any water will prevent xylene penetrating, and thus the section will not clear. Also remember your laboratory environment. Are you using xylene substitutes? Because xylene substitutes will take on more water. Any alcohol will absorb water from the environment. So just make sure that you are aware of the humidity in your laboratory, but storage conditions of alcohols, and make sure that you change at an appropriate time. So cover slipping. Absolute clarity with maximum resolution is required. The slide, cover slip and mountant must all have the same refractive index, and this minimises refraction at glass mountant section interfaces. Water must be completely removed. The clearing agent must be compatible with mountant. Just check if you have got a new mountant or you are thinking about a different clearing agent other than xylene, that you sometimes will have an incompatibility there. Make sure that your mountant is free of any crystalline structures. Make sure it's within its use-by date. Another thing that people commonly are very confused about is seeing the appearance of dark nuclei that appear to be for no good reason. And this is sometimes, we call it cornflaking, when that's actually air that's over the nuclei. And it's because the section has been allowed to dry out. And this could be in a commercial cover slipper or in a just in your staining, in your bench staining. But just be aware, if the slides do start to dry out, you might get these tiny little dark areas over the nuclei, and it's actually air. So recover slip. So some key points, and this is from the previous webinar to this webinar. It's really important to think globally to improve the quality. So you need to think of all of the different causes from both management level, which could be staff and training or fatigue, all of those kind of management level issues, as well as the myriad bench level issues that need to be considered. I really encourage a we can do it better attitude. Be systematic in your approach to quality improvement. So tackle one thing at a time and take it through to completion, but really give some thought as to where problems could be and what is consistent. Every step taken at the bench has an impact on quality, so all the staff must know. So optimising fixation and processing are essential first steps in improving quality. But as we've been through in today's session, you can see that there are other things that appear to mimic problems with fixation or problems with tissue processing that are actually caused by some very minor things, such as leaving a block in water for too long. Perhaps somebody's gone to tea and left some blocks soaking. Thinking about your balance of your hematoxylin and eosin, thinking about is your protocol for staining optimised on a cold slide or on a warm slide? So just these little things can make such an enormous difference to your quality within the lab. So that's my last slide. Questions?
Thank you, Fiona, for that informative presentation. We will now start the live Q&A portion of the webinar. And if you have any questions you want to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many questions as we have time for. So let's get started. We already have some great questions coming in from our audience members. Fiona, our first question is, my rodent tissue is dry and powdery after processing. We use a 12-hour protocol. What do you suggest for that?
Okay, so the first thing, rodent tissue is dry and brittle sometimes. 12 hours is a very long protocol for the size of tissue. And this is particularly, I would recommend optimising that tissue protocol. Many tissue processors nowadays are very efficient compared to some of the older dip and dunk with no heat, no vacuum, no agitation. So I think the first thing would be to optimise that tissue processing protocol to pull it back quite a bit. The other thing too is if it is dry and powdery, just using at sectioning some cold water on your block will actually help you get a section. So yeah, just try and sort of soften up that tissue so that you can recover it. But the best advice is optimise your tissue processing protocol.
Thank you so much. Our next question, how do you suggest we fix bone tissue?
Interesting question. So there's a lot of different types of bone specimens. So, and I talked about in the webinar, the first webinar, it's really about preparation of your specimen. So bone needs to be very well fixed, particularly if you're going to be decalcifying, to really protect it from the effects of decalcification. So if it's a large piece of bone, think about using a very fine saw to saw it. Just so that you expose the bone to a good fixative. Think about increasing the length of time that you would normally for a tissue, a soft tissue, just to make sure that there is time to penetrate. You could think about using an alternative fixative such as Davidson's, which is more an acetic acid alcohol formalin mixture. But again, the caution with any alternative fixatives is look at what the recommendations are. If you're making it up yourself or if there's a manufacturer for an alternative, they will recommend the time of fixation. And in the case of a Davidson's, don't leave it there for more than 24 hours before you then re-put it into a neutral buffered formalin or an alternative fixative.
Thank you so much. And I want to thank our audience for these great questions. Our next question comes from someone who needs some advice about their study. I'll share the study first and then give you the question. I'm studying the endocrine disruptor compounds related histopathological alteration in fish gonads and following the OECD guidelines related to the same. The OECD guidelines mention the fixation of gonads in Davidson for 24 to 48 hours and then subsequent washing and storage in 70% ethanol. However, I will be in the field for 2 months and there will be a gap of 3 months before I actually start the tissue processing histopathological examination. So kindly, could you guide and share your opinion if the storage of samples in ethanol for such long periods will have any effect in histology examination at cellular level? And what are the temperature conditions that should be maintained during preservation time? And thank you in advance for your guidance.
Wow. So it's a great question. I think, first of all, if you are following guidelines and if you're needing to do a particular study protocol, then follow the guidelines. Again, I mean, it's interesting. The Davidsons is, as I said, with many other of those kind of fixatives, they do have a limited time in which you should store your tissues. Putting it into 70%, that is an older technique, which I think some people still do, is to put it into 70% if they need to do IHC after the initial fixation. And this is because the first part of fixation with neutral buffered formalin is reversible. The second, as it gets stored longer and longer and more chemical reactions and cross-links occur, it becomes irreversible. So depending on what downstream process you want to do, you really need to think about the storage. In terms of temperature, again, it's really, if it's 70%, is it going to start evaporate? What will preferentially evaporate? You want to make sure that it doesn't evaporate so it's more water. You want to make sure that it is in a fixative. So yeah, my advice there is follow the guidelines, consider what your downstream processes are. In this case, it's very specific. Don't be afraid of 70%, but do make sure that you are in an airtight container or not in heated conditions. But yeah, follow the guidelines, I suppose, is really ask specifically what your study protocol requires.
Thank you so much, Fiona. And we have time for one more question. This audience member says, there are a lot of questions about specific protocols. Can you give me some general recommendations about protocols?
Yeah, I mean, it is so there's certainly in the previous presentation, I shared a theoretical theory of protocols, and where smaller tissues might require a shorter protocol, very large tissues might require much longer. And it's sometimes difficult to balance that when you have a mixed workload. Particularly if you're looking at research in more animal tissues, this can be even more varied than looking at human tissues. So I guess if you have a particular type of tissue, it is working towards optimizing within your laboratory, within the reagents that you are looking at using, some guidelines in terms of your ratio of alcohol to xylene and wax, which should be about a 1.5 to 2 to 1 to 1 ratio, is a good guidance. So yeah, I think the protocols themselves really have to think about, have you got one sort of specimen that you're processing? Have you got a mixture of different specimens? Have you got the luxury to separate out the specimens to different times or different retorts? And then think about what is best for that tissue. What is best for the laboratory too, in terms of xylene substitutes to xylene. Very important in terms of, how exposed staff is. So I guess it was a general questions and general answers on it, but effectively make sure you validate, make sure you optimize, particularly from what you want to do, and think about the ratios of your reagents, and think about the times if you're using things like xylene substitutes, which you will need longer times. Hope that helps.
Thank you so much, Fiona. And I want to thank you for your presentation today. Would you like to provide any final comments for our audience before we close?
Yes, as a last slide, I'd just like to show the audience. Okay, there are a number of references that are available on the Leica Biosystems website. In particular, there are 2 textbooks which are available to download as ebooks or to download and keep in your laboratory. So these were authored by Jeffrey Rolls, who was a senior lecturer at RMIT in histology, and they're really, really excellent books. So 101 Steps goes through just very basic tips, some of which I have covered here today, and difficult blocks and reprocessing. We'll talk you through some of the methods of reprocessing. There's quite a few decision trees that you need to go through. We shared some where if it's over-processed, reprocessing may not help, but then what do I do? If it's under-processed, what do I do? And that can be very specific to what's actually happened. Is it under-processed? Was it too large? Was it the wrong proportion? So have a look at these books and any other educational material. It can really help just to get some of these decision trees, think about what the next steps are, but also 101 Steps is hints and tips. So thank you. Thank you all. Thank you all for listening.
And thank you again, Fiona, for your time today and for your important research. Before we go, I want to thank our audience for joining us today and for their interesting questions and questions we did not have time for today. And those submitted during the on-demand period will be addressed by our speaker via the contact information you provided today at the time of registration. And we once again want to thank you all, and we want to thank our LabRoots and our sponsor, Leica Biosystems, for underwriting today's educational webcast. You can view this webinar on demand, and LabRoots will alert you via an email when it's available for replay. That's all for now. Until next time, everyone, take care, be safe, stay healthy. Bye-bye.
Thank you.